All right, so this section is about area and volume. Area and volume are old friends in terms of like math, I guess. Like you've done stuff with area and volume like all the time with geometry, and so we're going to use some of that geometry knowledge, a little bit of that like abstract reasoning, draw some tiny rectangles, and figure out stuff. All right, so let's try to do it. The key to success in this chapter is really to draw tiny rectangles, because what we do with definite integrals is that we're basically making an infinite number of tiny rectangles. And so when we're using integrals to find areas, or using integrals to find volumes, we are taking those tiny rectangles and we're doing stuff with them. We're either like adding them up, or we are rotating them, and then from that rotation we're figuring out the volume of like a what's the thing? A cylinder, and we're just doing that. So tiny rectangles, super duper helpful. So look at this picture. You can see that there are some different regions that are shaded. So here, this is the area between curve F and curve G. And how are we going to figure out what that area is? Well, we take the area under G, which is this part, all of that, which includes the area between and the area under F, right? So all of this, and then we're taking away the area under F, and so if we overlap those, if we subtract out, that's really not hard, that's difficult to see. If we subtract out this blue section, which I'm going to highlight in this whatever gold thing, if we take away that area, then we're just left with the area between, which is the yellow, which is what we wanted. So the way we can find that, the area between curves, is just taking the top function minus the bottom function and taking our definite integral of that. This works when we're looking at tiny rectangles that are vertical. So the area between these two curves, we can think about it in terms of like vertical rectangles. And so this works. We're looking at the height of the rectangle is the function f minus the function g. I think I mixed those up. G is the lower function, f is the upper function. Sorry, my bad. So we have the area under f is over here, the area under f is in green, and the area under g is in blue, and so the area between f and g is f minus g integral. And we're looking at the same bounds, right? A to b, A to b, A to b. That all works. And, I mean, that's just going between these two is just a property of integrals that we know, because addition and subtraction work with integrals like we think it will. So we can split up definite integrals between this function and that function, and then we can add them together, or this function minus that function and subtract them. So this isn't new per se, it's just a different visualization of what's happening. And we're looking at an area between now, and we can do that, which is cool. There is a thing in Desmos. I hope this works. This might work. So, look at this region where we have an upper function and a lower function, but it's kind of piecewise. So our lower bound, because this is this purple, I'm going to make that bolder. Okay, so we have this purple part, and we have this black part, which are both our lower bounds, and our red part is our upper bound. So in order to find the area bounded between these three curves, we need to think about it a little differently. We can either think with vertical rectangles, where we're looking at vertical rectangles like this. So we have like this purple region And so we're looking from 0 to 2, we can find the area between the red curve and the purple curve, which I'm coloring in green. And then we can find the area between the red curve and the black curve, so there's a tiny rectangle, which is determined by the difference in the red and the black curves on the region, on the bounds from 2 to 4, so this part. That is one way of thinking about it. However, that requires, a lot of, well, I guess it's subjective. If you can visualize it easier that way, then you can do it that way and just handle the two different regions, make sure that you add the green and the blue up together. Or you could think about it as just one area. But how could you do that? Well, if you think horizontally, so if you look at the distance this direction, so you set up your tiny rectangle. It's a really terrible tiny rectangle, I'm sorry. But if you set up your tiny rectangles so that they're going horizontally, so we're looking at a definite integral that is not in terms of x anymore, it's in terms of y. So we can look at that. All of this is just black curve minus red curve, right? This is the black curve minus the red curve because it's the height of all of our tiny rectangles that we have. So we can, with careful math, we can do an area between curves that's horizontal, which is nice, and you can also play around with this Desmos because it's pretty cool. You can have a representative rectangle show up with let's see. So we can have a representative rectangle where we're looking at the difference. So this is our tiny rectangle, and you can have this scrub back and forth. So this is fun to play with, and then you can also make it for the horizontal. You can have this scrub back and forth. So that's fun. All right. So when we're finding the area between two curves, let f and g be continuous and therefore integrable functions such that f of x is greater than or equal to g of x over an interval from a to b. So f is the bigger function. Let r denote the region bounded above by the graph of f of x and below by the graph of g of x, and on the right by the lines x, left and right by the lines x equals a and x equals b, respectively. Then your area is given by the definite integral from a to b of f of x minus g of x with respect to x. And if we're looking at a horizontal region, like if we're looking at this one, then the way that we would set this up is that we're saying that the area of f of y is greater than or equal to g of y. So that means that f is the right function, g is the left function. So we do, and then we have bounded by y equals a and y equals b. We have our definite integral where we have f of y minus g of y as our integrand, and we're doing this all with respect to y. And so that's going to give us the area as well if we're looking in the horizontal direction. So how are we going to find the area of the region bounded by the graphs y equals x squared plus 2, which is a parabola? We're going to do a quick sketch of that. So this is x squared plus 2. Y equals negative x. So that's negative x. And then x equals 0. X equals 0. And x equals 1. Well, we need to set up our definite integral. So we can look at our area. Let's do that in this Eagles green. No, it's not. It's like seafoam. Okay, so with this green, we're looking for that area. The area is going to be, well, our bounds are 0 and 1. And then our upper function is x squared plus 2 minus our lower function, which is negative x. And we're doing this with respect to x. And so what do we get? Well, minus a negative is plus, so we get integral from 0 to 1 of x squared plus x plus 2 dx. And does this make sense? Yes, because we have an area that's below the x-axis, right? But we want to count it as positive, so this minus a negative, that's okay. That still makes sense. We're adding in extra area. And then that's just power rule, right? So we go 1, oh, no, I don't want that, because I'm integrating. Fundamental theorem of calculus. So we got x cubed over 3 plus x squared over 2 plus 2x, and we're evaluating from 0 to 1. All those zeros are going to go away, so we're just left with 1/3 plus 1/2 plus 2. What is that? 6 is our least common multiple, so we get what? 3/6 plus 2/6 plus 12/6. 3 plus 2 plus 12. 17? 17 over 6 is our area between our two curves. This is the area of the region bounded by these graphs. All right. So how about this, where we have the area of the region bounded by 2 minus x squared, so that's the parabola facing downwards, and g of x equals x, so that's a straight line, and now we have an area. But we're not given our intersection points. We're not given our upper and lower bounds, so we need to figure that out. Let's figure those out. How do we figure those out? Well, we can just set these two equal, so we have 2 minus x squared equals x, and find out where they intersect. So we get what? 0 equals x squared plus x minus 2. Can we factor that? I think so. 0 equals x minus 2, x plus 1. Nope, I flipped the signs. X plus 2, x minus 1. Multiply. Okay. So that means that our solutions are 1 and negative 2. So our bounds are negative 2 and 1. And here we go. So we got negative 2 to 1, and our upper function, our top, is f of x, and our lower function, our bottom, is, that looks like a pie. Our bottom function is x. So we have 2 minus x squared minus x. And we're doing this with respect to x because our tiny rectangles that we can draw are vertical tiny rectangles. Okay, so that's power rule again. Let's see, we got negative x cubed over 3 minus x squared over 2 plus 2x, evaluating from negative 2 to 1. That's negative 1/3 minus 1/2 plus 2 minus parentheses. We got this negative 2 that we're cubing, so this negative 8, but negative that is 8/3 minus 4/2 minus 4. And then we evaluate that, and we get numbers, let me see. Well, so this what? Negative 1/3 minus, or plus 3/2. I'm just combining those two. And then minus 8/3 plus 2 plus a 4. So we get, well, these two put together are negative 9/3, so that's negative 3. Plus 2 plus 4, that's positive 3, plus 3/2, that's positive 4.5. And we're just going to be lazy, 4.5. Okay. Efficient. We're going to be efficient. And does that make sense? I think so, because we need a positive area. How does that compare with what we had before? That's like less than 3, but that also makes sense because our region is kind of smaller. Yeah. So in general, when we're doing our area between curves, we are either doing our integral of top function minus bottom function when we're integrating with respect to x, and we have our bounds in terms of x, so these are x1 and x2. Or we are doing an integral of our right function minus our left function when we're integrating with respect to y, and when these bounds are y values, y1 and y2. So top minus bottom or right minus left, because it's the greater value, a greater function minus the smaller function. Alright, so how are we going to find the area between the graphs of x equals 3x cubed minus x squared minus 10x and g of x equals negative x squared plus 2x? Well, this is cubic. Oops. This is cubic, and this is quadratic. And it seems like, well, we can factor this, right? We have f of x is x times 3x squared minus x minus 10. And that seems like, okay, so that's it's a cubic kind of going like this. And where our intersections, oh, well, we drew that poorly. Because we're going through here. And then we can find our, oh, interesting. Because we know that x equals 0 is the intercept. And then look at g. We also have an x-intercept for g at 0. So if we have intercepts is 0, and this is going to give us, what, positive 2 as an intercept. So we have g looks like that, and then f is going to look something maybe like that. We might get actually like two different regions that are bounded by these curves. So how do we reconcile that issue? You just split it up into two parts. So look down here. Oh, lovely. Okay. So we have intercepts at x equals negative 2, 0, and 2. And let's just verify that that makes sense. We have 3x, so this is really difficult very easy to see, but difficult to manage space. 3x cubed minus x squared minus 10x equals negative x squared plus 2x. And so we already know that x factors out of these, so we're just going to factor that out and say that x equals 0 is going to be a intercept. So we have 3x squared minus x minus 10 equals negative x plus 2. Let's combine some like terms, so we get 3x squared plus x, and that actually cancels out everything, and then a minus 2, so we got minus 12, and then equals 0, so then we GCF this, x squared minus 4, and that's a difference of squares, 3x plus 2, and then 3 is already there, x plus 2, x minus 2 equals 0, so we also have x equals negative 2 and x equals positive 2 as two more intersections. Okay, so we need to set up two different definite integrals. So we need to look at the region between, let's look at the picture. So we got the region between negative 2 and 0, and what is our top function there? Well, if we don't know, then we can plug in a number, plug in like 1, into both g and f. So plug in 1 to g, and you get negative 1 plus 2 is, no, negative 1 minus 2 is negative 3. Plug in negative 1 here, you get negative 3 plus minus 1 plus 10, which is 6. So that means that f is the top function. So f is 3x squared minus x, or 3x cubed minus x squared minus 10x. This is our f. Minus g, and I'm going to throw parentheses around this, and I strongly recommend that you do so as well. Put parentheses because otherwise you're going to lose track of your negatives. And we have our g function, which is negative x squared plus 2x. And doing that with respect to x. And that is the left region. But after we cross the origin, we're going to have a different region with a different upper bound, upper function. Like our top function is going to switch. So from 0 to 2, our top function is going to be g of x. So we have negative x squared plus 2x minus our bottom function, which is f of x. And I'm going to use parentheses because it's responsible. 3x squared minus 3x cubed minus x squared minus 10x. We're doing this still with respect to x. And from here, just combine some like terms and do some power rule, which you should be familiar with by now. Alright. So, once again, we have top curve minus bottom curve for when we're looking at like a vertical region where you have vertical rectangles, and right curve minus left curve if we have some sort of horizontal region. And it's like sometimes it's easier to just do one versus the other. Other times it doesn't really matter. So just be careful and think ahead a little bit before you try tackling any of these, so that you can try to figure out which direction to go. Alright, so finding the area bounded by the graphs x equals 3 minus y squared, which is that, and x equals y plus 1, which is that. So since we have our x equals, that probably means that it's easier to handle going in the horizontal direction because what we're changing is y. Like what our input is y, so we don't have to do any algebra to just solve this in terms of y. Also, there's like this whole part, which if you're looking at it vertically, you're looking at the difference between like a plus and a minus of a root function, and that's just like, too much effort. So let's look at this horizontally. Which function is on the right? Well, if you don't know, oh yeah, we also need to find our intercepts. So we got what? 3 minus y squared equals y plus 1. 0 equals y squared plus y minus 2. And that we can factor y minus 2, no, y plus 2, y minus 1. Hey, it's the same as one of the ones above. Okay, so we got intercepts at negative 2 and positive 1. And what's further to the right? Well, what's between negative 2 and 1 that's easy to plug in? I would say 0. So plug in 0, 0 there and there, and what do we get? 3 and 1. So this function, 3 minus y squared, is the greater function. And I'm going to put parentheses with my y plus 1. And we're integrating with respect to y. Okay, so then we just do that. And again, this is just power rule. I guess since it's in terms of y, we should do it for good measure. But negative 2 to 1, and we have 3 minus 1 is 2 minus y squared minus y dy. And power rule this. Oh. We have 2y minus y cubed over 3 minus y squared over 2 from negative 2 to 1. plug those in, we get 2 minus 1/3 minus 1/2 minus parentheses, negative 2 times 2 is negative 4 plus 8/3 minus 2. Yeah. Simplify that. Let's see, what is that? 3/2 minus 1/3 minus, no, plus 6 minus 8/3, and that's 3/2 plus 6 minus 3, 3 plus 3/2, which is 4.5, and that's the same. Interesting. It's almost as if when you rotate an area, like when you rotate a shape, the area is the same. It's wild. Alright. So, another thing is that accumulation is, accumulation is a vocabulary that we like to use with integrals. And we're finding the area of the region bounded by our graph, which is a parabola, and the x-axis. And we're going to try to describe this as an accumulation process. And the way that we are going to think about this is that you are accumulating, or you're acquiring or gradually gathering areas of rectangles. And so you can think about accumulation in terms of integrals, because when you're looking at, like, as you are going through, moving from left to right, as you're moving through your region, you're taking tiny rectangles, and you're taking those areas and you're adding them together. So eventually you'll have added up all the tiny rectangles of that region. And this has applications in other things, as long as we have some sort of way of describing what the behavior of something is, and so that we can see like how much something has accumulated. Because like if you know like the current number of if you know the number of like people who are entering into a building, and then you add up the people who are entering into the building, then you have accumulated the total number of people in the building if it was empty in the beginning. And so, you know, if you're looking at figuring out how many people are like in a football stadium, then you can just count as they're coming in, add up like how many people entered per minute, and then for however long people are entering, and then there you go. Or like, you know, other applications of that. There's other applications. Should maybe look some up. Think about it for a math journal. Sounds like fun. Alright. So here is a picture of that. So we have an accumulation of the areas of these rectangles, and we're adding them up. So like as we're moving forward, oh wait, which direction? As we're moving forward, like we're moving, imagine you are on the number line and you're moving and adding up the rectangles as you're going past all these different places. This rectangle, this tiny rectangle is going through, and you're like adding up all of those areas of those tiny rectangles. I guess we can call it a representative rectangle. I don't know. Tiny rectangle is fun. So, accumulation is when you're looking at an integral as you're moving. How do you find the region R for this picture? There's a couple of options. You can either look vertically and look at your definite integral from 0 to 1 of f of x, and then look at your definite integral from 1 to 3 of g of x. Or you can look at a horizontal tiny rectangle, so that you're looking at the difference in your y's, which takes a little bit of algebra. What's that, like y minus 3 halves and then multiply by -2, so plus 3 is g. And then f of y is just going to be y squared, right? So that's a parabola. So, look at that. Let's just do that one. And where that those intersect at 1? 0 to 1. Okay, so we got from 0 to 1. 0 to 1, and we have our right function is g of y, so we have -2y plus 3 minus our left function, which is y squared, and that's only one term, so I don't need to have parentheses, dy, although you could if you want to. So what's that? Negative y squared plus 3y minus y cubed over 3 from 0 to 1. And that's just -1 plus 3 minus a third, minus 0. 2 minus a third is 6 thirds, no, yeah, 6 thirds minus 1 third is 5 thirds. 5 thirds is our area. So we did a little bit of algebra in the beginning so that we could have less algebra in our definite integral, but you could also split this up so that we have integral from 0 to 1 of root x minus 3 halves minus x halves dx plus integral from 1 to 3. Oh, no minus of that. We just have, it's just f. So we have dx plus our integral from 1 to 3 of g of x, which is 3 halves minus x halves dx. Either way, up to you. Alright, I think we're stopping at that. We'll make another one for volumes.